Yes. Metronome. Arkadaşlar tekrar hızlı yapıyorum. इतना तो चमकते। all the techniques you have to learn. The just Calculated AI. Come together right now. Over.
Hello and welcome to Multivariable Calculus.
No, not yet.
Welcome to all.
No, yet. No, 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 not yet. Two hours and 14 minutes.
In this video,
Oh hell no, 1 hour.
How should we define?
One hour and 41 minutes.
Hey guys, so
let's work on this.
together right now. Oof. Okay, let me just do Duolingo for now. I'm not in the mood only. Duolingo. I'm not in the mood. What? One.
Anna.
Anna.
Ich bin Karl.
Ich bin Karl. Karl.
Wasser.
Und
Ich. Wein.
ein Vater.
Ein Vater.
Hallo, ich bin Anna.
Eine.
Hallo, ich bin Anna.
Ich bin Nina. Ich. Hallo, ich bin Karl. Eine Mutter und ein Vater.
Eine Mutter, ein Vater.
4.
Comment ça va?
Oui.
Bien.
Comment?
Bonjour.
Ça.
Oui.
Oui.
Où.
Oui, suis. Oui. Ça va bien?
Bonjour, Marie.
Bonjour.
Bonjour.
Bonjour, comment ça va?
Comment? Ça va, Paul. Leche.
Hola. Pan.
Agua.
Hola, buenos días. Ella, hola.
Adiós. Agua. Niña.
Leche.
Adiós. Comes. Noche.
Buenos días.
Buenos días.
Hola, mucho gusto.
Buenos días.
Gracias. Buenas noches.
Hola, soy Dora.
Gracias.
Gracias a Dios.
Adiós. Gracias. Buenas noches.
Buenas noches. Buenos días.
Buenos días, mucho gusto.
Buenas noches, buenos días. Mucho gusto. Buenos días. Buenas noches. Buenos días. Ok.
Mucho gusto.
Come together. Oh. Itu apa? After I finish Italian, I'm gonna start.
Ciao, Luca.
Salve. Io.
Ciao,
Ciao, Anna.
io sono Luca. No, io.
Sì, Luca, per favore.
Anna.
Sì, Anna, per favore. Ciao, io sono...
Ciao, io sono Luca. Io sono Luca.
Cielo. Cielo. Tonno. Tonno.
Salve. Io sono Luca.
Oh. Wrong direction. Per favor. Or for flavor.
All of Calculus 3 in 8 minutes. Disclaimer, I could not fit absolutely everything in here, as it would make the video way too long. Thanks to Fuzzy Penguin AMS for inspiring this video. Check out their video on Calc 2, which I've linked in the description. Now let's get into it. Part 1. 3D space, vectors, and surfaces. Just like in 2D, there exist functions in 3D. These functions take two inputs on the x and y axes, and produce an output on the z-axis. Vectors are quantities with direction and magnitude. This also applies to 3D vectors, just their direction is three-dimensional. Part 2. Vector multiplication. We can do operations, like addition and subtraction, with vectors just like one would with regular numbers. What's different with vectors, though, is that there are different types of multiplication. The first is called the dot product, and it's the most intuitive. Just multiply each of the numbers in a vector by the corresponding one in the other vector, add the results up, and that's your dot product. This may seem arbitrary, but there exists an interesting connection between dot products and the spatial relationship between two vectors. Two perpendicular, or orthogonal as they're called in 3D space, vectors will always have a dot product of 0. For two parallel vectors, the dot product is equal to the product of the magnitude of the two vectors. This property extends to become the following formula, where theta is the angle between the vectors u and v, and the double absolute values mean magnitude of. The cross product is the other main way of multiplying vectors. This product can be expressed as the determinant of this matrix, where I, j, and k are the unit vectors in each of the x, y, and z directions respectively, and v and u are the vector being multiplied. The cross product also has an interesting property. It always generates a vector that is orthogonal or perpendicular to the two vectors being multiplied. Part 3. Limits and derivatives of multivariable functions. Just like with 2D functions, where we approach an x value, we can take the limit of a 3D function, where we approach a value on the xy plane. Using these limits, we can also define a derivative, just like one would in 2D. One thing to note is that there are infinitely many derivatives of a 3D function at a certain point, since there are infinitely many directions one can go in. Each of these are called directional derivatives. Also, taking the partial derivative with respect to x gives us the derivative in the positive x direction, and differentiating with respect to y gives us the derivative in the positive y direction. The gradient is a generalization of this. Gradient at a point is a vector with components being the derivative in the x direction and y direction. Part 4. Double integrals. Just like we define differentiation, integrals also exist with multivariable functions. When doing a double integral, instead of finding the area under a function, we're finding the volume under it. To do this, first do an integral in the x direction, and then integrate that area a second time over the y direction, effectively extruding it. But that isn't all we can do with double integrals. You can also integrate over a non-rectangular region. Instead of having the bounds of the integrals be numbers, they can be functions. We can also use polar coordinates for double integrals, where instead of making an integral dy dx, it is dr d theta. Notice that the polar equation we're integrating is r cubed instead of r squared. More on that later. Part 5. Triple integrals and 3D coordinate systems. Triple integrals can also be used for volume. With triple integrals, we can integrate any 3D region as long as we can define it with 3 different boundaries instead of 2. Here, x goes from 0 to 2, y goes from 0 to x, forming a triangular base, and z goes from 0 to y squared, creating a sort of parabolic shape. Triple integrals can also be used for finding things like average temperature, where we would integrate the temperature function over a 3D surface to find the average temperature. When doing a double integral, sometimes it's easier to convert to polar coordinates. Likewise, there's an analogous system in 3D space, or rather 2 analogous systems, cylindrical and spherical coordinates. In cylindrical coordinates, there is a radius r, a z-coordinate, and an angle theta. In spherical coordinates, there is a radius and 2 angles. Rho is the 3D distance from the origin, phi is the angle from the vertical line which passes through the origin, and theta works just like in polar. Part 6. Coordinate transformations and the Jacobian. There's actually an infinite number of coordinate systems, not just the ones described previously. Any coordinate system can be defined as x equals g of uv and y equals h of uv. As an example, in polar coordinates, this is x equals r cosine theta and y equals r sine theta. When changing an integral from one coordinate system to another, one must add a certain function j, the Jacobian, to the inside of the integral to account for the distortion that switching coordinate systems creates. Let's do this for the example of a double integral shown earlier. Here we can see the Jacobian being added to the inside of the integral. What I just said is basically an oversimplification of the reason behind the Jacobian, and the real reason involves a ton of cool math with matrices where the Jacobian is a determinant, but that could be an entire video of its own. Anyways, here are the transformations needed to convert to polar, cylindrical, and spherical coordinates. Part 7. Vector fields, scalar fields, and line integrals. A vector field is an assignment of a vector to each point in a plane or space. A scalar field is essentially that, but with regular numbers, aka scalars. Think of these as 3D surfaces above a 2D plane. In a way, they're essentially the same thing as 3D functions. When you take an integral in Calc 1, the integral is always done on a flat surface, think sheet of paper. What if this sheet of paper was bent in 3D space? This is a scalar line integral. These integrals are done over a scalar field. And yes, there are also vector line integrals done over vector fields. These can be hard to illustrate though, but you can think of them as the work done on a particle as it travels along a vector field of a force. Vector fields can be conservative, meaning that any line integral on them is path independent. This is very analogous to conservative forces, i.e. gravity, where the work done on particles is path independent. And in fact, gravity has a vector field, although this field varies depending on the objects that are present. Vector fields have two main properties, divergence and curl. Divergence is the amount of outflow from a certain part of a vector field. In the center, the divergence is high since everything is moving outwards, while further away, the divergence is lower since some points are moving in and some are moving out. Curl is the amount of rotation around a certain point in a vector field. Here on the outside, the curl is low since there is not much spin. But at the center, the curl is high since everything spins around it. And that's it. Once again, I left out a lot of stuff, as after all, you aren't supposed to learn this course in 8 minutes anyways.
So I think I should probably start off by addressing the elephant in the living room here. I am sadly not Sal, but I'm still going to teach you some math. My name is Grant. I'm pretty much a math enthusiast. I enjoy making animations of things when applicable, and boy is that applicable when it comes to multivariable calculus. So the first thing we got to get straight is, what is this word multivariable that separates calculus as we know it from the new topic that you're about to study? Well, I could say it's all about multivariable functions. That doesn't really answer anything, because what's a multivariable function? And basically, the kinds of functions that we're used to dealing with in the old world, in the ordinary calculus world, will have a single input, some kind of number as their input, and then it outputs just a single number. And you would call this a single variable function, basically because that guy there is the single variable. So then a multivariable function is something that handles multiple variables. So, it's common to write it as like x, y. It doesn't really matter what letters to use. And it could be, x, y, z, x1, x2, x3, a whole bunch of things. But just to get started, we often think just two variables. And this will output something that depends on both of those. Commonly it'll output just a number. So you might imagine a number that depends on x and y in some way, like x squared plus y. But it could also output a vector, right? So you could also imagine something that's got multivariable input, f of x, y, and it outputs something that also has multiple variables. Like, I'm just making stuff up here, 3x and, 2y. And this isn't set in stone, but the convention is to usually think if there's multiple numbers that go into the output, think of it as a vector. If there's multiple numbers that go into the input, just kind of write them more sideways like this and think of them as a point in space. Because, when you look at something like this, and you've got an x and you've got a y, you could think about those as two separate numbers. Here's your number line with the point x on it somewhere. Maybe that's 5, maybe that's 3, it doesn't really matter. And then you've got another number line, and it's y. And you could think of them as separate entities. But it would probably be more accurate to call it multidimensional calculus, because really, instead of thinking of, x and y as separate entities, whenever you see two things like that, you're going to be thinking about the xy plane and thinking about just a single point. And you'd think of this as a function that takes a point to a number, or a point to a vector. And a lot of people, when they start teaching multivariable calculus, they just jump into the calculus. And there's lots of fun things, partial derivatives, gradients, good stuff that you'll learn. But I think first of all, I want to spend a couple videos just talking about the different ways we visualize the different types of multivariable functions. So as a sneak peek, I'm just going to go through a couple of them really quickly right now, just so you kind of whet your appetite and see what I'm getting at. But the next few videos are going to go through them in much, much more detail. So first of all, graphs. When you have multivariable functions, graphs become three-dimensional. But these only really apply to functions that have some kind of two-dimensional input, which you might think about as living on this xy plane, and a single number as their output. And the height of the graph is going to correspond with that output. Like I said, you'll be able to learn much more about that in the dedicated video on it. But these functions also can be visualized just in 2 dimensions, flattening things out, where we visualize the entire input space and associate a color with each point. So this is the kind of thing where you'd have some function that's got a 2-dimensional input. It would be f of x, y. And what we're looking at is the xy plane, all of the input space. And this outputs just some number. Maybe it's like x squared. This particular one is an x squared, but that and maybe some complicated thing. And the color tells you roughly the size of that output. And the lines here, called contour lines, tell you which inputs all share a constant output value. And again, I'll go into much more detail there. These are really nice, much more convenient than 3-dimensional graphs to just sketch out. Moving right along, I'm also going to talk about surfaces in 3-dimensional space. They look like graphs, but they actually deal with a much different animal that you could think of it as mapping 2 dimensions. And I like to sort of spush it about. And we've got kind of a 2-dimensional input that somehow moves into 3 dimensions. And you're just looking at what the output of that looks like, not really caring about how it gets there. These are called parametric surfaces. Another fun one is a vector field, where every input point is associated with some kind of vector, which is the output of the function there. So this would be a function with a 2-dimensional input and then 2-dimensional output, because each of these are 2-dimensional vectors. And the fun part with these guys is that you can just kind of imagine a fluid flowing. So here's a bunch of droplets like water, and they kind of flow along that. And that actually turns out to give insight about the underlying function. It's one of those beautiful aspects of multivariable calc. And we'll get lots of exposure to that. Again, I'm just sort of zipping through to whet your appetite. Don't worry if this doesn't make sense immediately. And one of my all-time favorite ways to think about multivariable functions is to just take the input space. In this case, this is going to be a function that inputs points in 2-dimensional space, and watch them move to their output. So this is going to be a function that also outputs in 2 dimensions, and I'm just going to watch every single point move over to where it's supposed to go. These can be kind of complicated to look at or to think about at first, but as you gain a little bit of thought and exposure to them, they're actually very nice, and it provides a beautiful connection with linear algebra. A lot of you out there, if you're studying multivariable calculus, you either are about to study linear algebra, or you just have, or maybe you're doing it concurrently. But understanding functions as transformations is going to be a great way to connect those two. So with that, I'll stop jabbering through these topics really quickly, and in the next few videos, I'll actually go through them in detail, and hopefully you can get a good feel for what multivariable functions can actually feel like.
In this lesson, we're going to focus on finding the limit of multivariable functions, if it exists. If it doesn't, we need to show that it doesn't exist.
Yes. Go back to base. There goes my hero. Come together. Right now. watch this and this is like 19 minutes. I'm gonna do like around 1 hour 20 minutes ish on this on 2x speed. Yeah, 2x speed, 1 hour and 20 minutes of this. Then I'll go here. Let's watch this at 2x speed and this. Yeah, that makes sense. Okay.